A language model prompted to think step by step generates pages of logic. But when internal representations detach from external facts, the logic spirals out of control. This highlights the limitation of pure chain-of-thought prompting. The model acts as a static black box, reasoning entirely over its own internal generations, rather than interacting with the outside world. Because it never checks its assumptions against reality, a single fabricated detail early in the chain is treated as absolute truth, compounding into massive hallucinations by the final output. The traditional alternative is act-only prompting, where a model is trained to strictly emit tool calls and interact directly with an environment. But an agent that only acts lacks an internal reasoning trace. It cannot formulate a long-term plan, keep track of intermediate subgoals, or figure out what to do when a tool returns an unexpected error. In a 2023 paper from Yao et al. Titled ReAct, researchers proposed an architectural bridge to merge these two isolated capabilities. The solution is structural. ReAct unifies thinking and doing by treating an internal reasoning step as just another functional action, specifically an action that the external environment simply ignores. In a standard agent environment loop, a controller evaluates a state and selects from a predefined action space, designated as A. These are physical or digital tasks, like clicking a button or executing a search query. Separate from this is the unbounded language space, designated as L. This space handles free-form reasoning, planning, and goal decomposition. ReAct combines these two domains into an augmented action space, represented mathematically as A hat equals A union L. When the controller selects a thought from space L, it produces no external observation. The environment does not respond. The thought simply appends to the agent's internal working context. When the controller selects a task action from space A, it strikes the environment and returns real external data as an observation. Because both options are selected from the same mathematical set, the architecture does not require a separate reasoning module to supervise the tool use. By treating language as a valid move in the action space, a single frozen large language model can interleave complex reasoning and concrete actions through the exact same emit step interface. To execute this loop, the model starts with a context window containing the user's task and a few handwritten trajectory examples. A frozen LLM, the original paper used Palm 540B, evaluates the context and decides whether the next best step is an internal thought or an external action. For knowledge-intensive tasks, the model adopts a dense alternating rhythm. It generates a thought, executes an action, receives an observation, and immediately generates a new thought to evaluate that data. For long-horizon decision-making tasks, like navigating a simulated household, thoughts appear sparsely. The agent executes multiple actions in a row and only pauses to think asynchronously when it needs to course-correct. To force the model to actually use this reasoning capability on knowledge tasks, the researchers restricted it to a highly constrained Wikipedia API, providing only basic search and lookup commands that return a few sentences at a time. If a user asks, "When did Frida Kahlo die?" the model first generates a thought stating that it needs to locate her biographical entity. It then emits a search action for her name, hitting the external Wikipedia environment, which returns an observation containing her birth and death dates. This factual observation updates the context window. The model recognizes it has the necessary data, formulates a concluding thought, and emits a final action to terminate the loop and output the date. The deliberate weakness of the retrieval API ensures the agent cannot rely on a powerful search engine to do the heavy lifting. It must explicitly formulate subqueries and synthesize the pieces itself. But absolute grounding comes at a cost. By forcing the language model to abide by strict API rules and external validation, it loses the fluid flexibility of unbounded logic. ReAct trades hallucination for reasoning errors, failing 47% of the time versus COT's 16%. This rigid structure frequently stalls the agent, trapping it in repetitive cycles that continuously emit the same search query, yielding no new data. Because of these cascading reasoning errors, pure ReAct actually slightly underperforms pure chain of thought in total accuracy on the Hotpot QA benchmark. To fix this, engineers fuse ReAct with chain of thought self-consistency. If ReAct hits a step cap without answering, it falls back to self-consistency logic. Conversely, if self-consistency lacks a high-confidence majority, the system defaults back to the firmly grounded ReAct loop. Implementing this on smaller parameter models requires fine-tuning on thousands of bootstrap trajectories, because models under 62 billion parameters struggle to learn both reasoning and acting simultaneously from simple prompts. Absolute grounding eliminates hallucination, but its inherent rigidity requires architectural fusion. Robust systems don't rely on one method alone. They dynamically switch between the fluid logic of unbounded thinking and the strict verification of action.